In this session, we will use the Thinkat software to illustrate how to compare numerical results and analytical results. So the focus is in describing or comparing the analytical and numerical simulation for projectile motion. So here we have fixed the canvas 400 by 30. So it's the same as the code that we use in rectilinear motion. And then we initialize the position and velocities. So we have two objects. So we will use ball 1 for the numerical simulation and ball 2 for the analytical simulation. And the box is represented as a plane, or the plane for the ground level. So we have a plane and the balls are at the origin, vector 0, 0. So both yellow and green are on the same position. So you have overlap position for the two. So if you separate them, you just need to change the position of the other vector. So let's say ball 1 is vector 2, 0, 0 plus the origin. Now you have separate locations. Okay. So since we want to compare analytical and numerical results, we will use the same initial conditions. So to simulate this, we initialize the simulation at time equals 0. And then we increase the time step. dt is, say, 0.01. Okay. So first, we simulate the numerical part. So while the ball is above the ground, it will perform the simulation. So we use while ball 1 dot pos dot y is greater than or equal to 0. So we need to put the condition equal to 0 because the initial position is 0. Then we fix the rate to 100. So 100 computations per second. And then the numerical updates equations will be first for the velocity update equation. Velocity of ball 1. So ball 1 velocity is equal to ball 1 velocity plus 80 acceleration times dt. So outside the while loop, we can define the acceleration vector equal to negative 9.8. So 0x, negative 9.8y, and 0z. And then the position update equation. We have ball 1 dot position is equal to ball 1 dot position plus the velocity, ball 1 dot velocity times dt. And then we increase the time step for t time plus dt. So that's the first simulation. Okay, this should be ball 1 dot pos. Okay. So we include a trace for the objects. Make trail is equal to true. Same with the other object. Okay. And the ball stops upon reaching the ground. Okay. Next is to plot the analytical expression. So you calculate the analytical equation based on the second law of motion. So the equation of motion will be integrated twice to get the position. For the velocity, you need to integrate it once. So ball 2 dot pos is equal to the initial position. So you don't need an update equation for the position and velocity. You just need an equation for the time update. R0 plus velocity times time, because here you are mapping or plotting the equation, times 1/2 or plus 1/2 times acceleration times time square. And the velocity, ball 2 dot velocity is equal to V naught plus acceleration times time. So now you have the two quantities being simulated. So in the analytical result, you just write the equation as is, and the position and velocity are constants. R0, or I mean the initial velocity and the initial position should be retained as constants. So to compare the two simulations, you can add a graph. So since you will compare position and compare analytical and numerical values for position and for velocity, use two graphs. The first graph is for position versus time. The second graph is velocity versus time in meters per second. So for the position versus time, so we compare x values. We have g dots, or you can use g curve. So we'll use the same color code. Numerical for yellow. For graph 1. And then the red one will be the analytical or theoretical. Um, and theoretical. Okay. And then just call the plots inside the while loop. So position x versus time dot plot time and ball one dot pos dot x. Okay. So let's try the first one. So this should be the numerical one. Table num. You should put equal sign. So use color equals color dot green and color dot yellow. Okay. So the position in X should be linear. Okay. But you can see that there are discrepancies with respect to Y. Let's see if we can actually see that. So let's check Y. So palitan natin to. Ball1 dot pos dot Y. Okay, so we have a parabola. So let's map also the theoretical ball2 dot pos dot Y. So initially, you have differences in values. Then after some time, you get a difference in the numerical values for the final position. So check whether there is an effect if we change the time step. So as you increase the time step, you also increase the computation rate. Or as you decrease the time step, you increase the computation rate. So the initial values now match with each other, as you can see, by increasing the time step. So let's see if it also works for uh, larger values of time until it reaches the ground. So we will also do this for the velocity. So velocity versus time. Then we use graph 2. So let's see first the x position. So velocity versus time. So now we call for the velocity attribute. And check the x component. Velocity dot x. Okay. So let's comment first the position plot. So here we have a straight line. That's because of the same velocity that we use, which is 1 meter per second. It did not change with time. So let's check. V0 is equal to 1 and 10. Okay. So there's no acceleration in the x direction. So you expect constant velocity in x. Okay, we increase more the rate of computation. And then verify y and compare them. So the slope is negative. So if you decrease or increase the time step 0.01, let's see if there is a discrepancy. So it's the same discrepancy that we expect for the position. They may overlap kanina, and then we have different values for y and v. Okay. So these are the position and velocity plots for the numerical and theoretical results. So let's bring back to 100. Check if we see realistic motion. Okay. So you can minimize the discrepancy as you increase the time step. So if you use momentum update equation instead of velocity update equation, you need to use the mass attribute of the object. So you need to define the momentum. So ball1 dot p is equal to ball1 dot mass times ball1 dot velocity. Then we will have the same equation for ball2. So instead of acceleration, we use force. So gawa na lang tayo ng panibagong line for the force. So force is equal to mass times g. All one dot mass times g. So force 1, and then another force for the theoretical, but they are the same. So you can equate force 1 and force 2, but let's generalize it. If you have multiple particles, you can also use this one. So instead of using ball 2 as the theoretical object, it can be another object that is uh, or that will be simulated numerically. So the velocity update equation now becomes the momentum update equation. So ball 1 times, or ball 1 dot momentum plus force 1 dt. And then for the position update equation, this will be momentum divided by the mass. Okay. So the same with uh, ball 2, but now we have the update equation in terms of position and velocity. So there's no need to put it in terms of force and momentum because these are now your kinematic equations. Let's just increase the rate and then run again. So dt is not optimized in this case. So we still expect the same discrepancy between the theoretical and um, numerical result. So we need the acceleration vector for the velocity and ball 2 position. Okay, so let's check where is the discrepancy between the two. Now we have the numerical value to be offset with respect to the theoretical. Okay. So this one should be in line 36. This should be momentum update, not velocity. Okay. So that's how you will compare the numerical and analytical results. So you can refer to the other tutorials and you can put the equation of motion or the force inside a function.